Good morning, my name is Eduardo Barrera. I'm a PhD candidate in Jonathan Boss Group. In this presentation, I'm going to talk about the work that we have done fabricating and characterizing metal oxide semiconductor quantum dots, with the ultimate goal of implementing spin qubits. So I'll begin by talking about what is quantum computing and silicon qubits. Then I'll move on to fabrication and experimental results. This will lead us into a discussion of readout techniques and what a universal quantum processor is. And then I'll finish off with some remarks about error correction, some of the challenges that we still have, and some conclusions. So what is quantum computing? When we think of a classical computer, we think of classical bits, 0 or 1. In a quantum computer, however, you have qubits. So they are any physical quantum system that has two dimensions. And because it's a quantum system, then you have the property of superposition, which means that it can be in a state of that it's a linear combination of 0 and 1. So if we visualize this in a Bloch sphere, it would mean that the north and the south are the classical bits, and any point on the surface of the sphere, it's a qubit. Now, if you were to imagine that you had n qubits in a 1D array, then the real power behind quantum computation becomes apparent, and it's essentially the fact that these n qubits can be in a state that's in a superposition of a total of n possible values, 2 to the n possible values. This essentially means that if you wanted to emulate this with a classical computer, you would need 2 to the n classical bits. And if you had 64 qubits, that's already beyond today's technology. So the property of superposition is really the reason why so much interest has been gained with quantum computers. Now, I like to point out that in this sort of setup with these n qubits, if you had arbitrary single qubit control and a 2-qubit entangling gate between neighboring qubits, then you could actually implement any arbitrary n qubit operation, and you would have a universal quantum processor. And we'll go back to this idea towards the end of the presentation. Now, a very natural application of quantum computation is to do quantum simulations, because essentially there's a linear mapping between the size of the system you want to simulate and the number of qubits that you need. Now, there's different types of qubits. You have superconducting qubits, ion traps, nitrogen vacancy centers in diamond, NMR, and also an electron spin qubit. Now I'll focus on a type of a spin qubit where you use gate-defined quantum dots. So in a gate-defined quantum dot, you essentially have a single well potential that confines an electron, and the electron can only be in discrete energy levels. These levels are doubly degenerate because of the spin of the electron, but we can lift this degeneracy by applying a magnetic field, and that's where the spin qubit emerges, in this 2-level quantum system that is essentially the state of the spin state of the electron, which obviously can be parallel or antiparallel to the magnetic field, or a superposition of the two. Now, the single wave potential can be achieved using a suitable metal geometry in a semiconductor material. Several types of semiconductors have been used to do this, but silicon really stands out as an ideal candidate to develop a physical qubit, because it has long spin coherence time in isotopically purified silicon. It is very compatible with CMOS circuitry, and it has great promise to scale up because of all the technological innovation that has been occurring in the semiconducting industry. So this last point is very important, because the most difficult problems that are of interest to researchers, they would actually require, and that cannot be solved with classical computers, they would require a quantum computer that has millions, if not billions, of qubits, and therefore solving this scaling problem it's really important, and this is also why silicon has been seen as a possible solution to this problem. Now I'll say a few more things about quantum dots. So as I said, you use gate geometry to define the quantum dot. We do this by applying voltages on these gates. This gives us control over the potential shape of the quantum dot, the chemical potential of the dot, and also its electron occupancy. If we now were to apply a bias, we open up a bias window, and if the chemical potential of the dot lies within this window, then you have electron transport. This is shown on the top left image. If otherwise this is not the case, then current is not allowed to flow. If you then look at the current through the dot as a function of this controlling voltage, which is usually called plunger voltage, then you would see a series of peaks called Coulomb peaks, or referred to as Coulomb peaks. So on each peak, you have fluctuating charge in the dot. This is because current is allowed to flow. And then in the regions of zero charge, you have a stable, fixed amount of charge, or number of electrons. This phenomenon is called Coulomb blockade, and is very important for what we want to talk about. Now, the separation between peaks also tells you about the charging energy of the dot, which can be related to the confinement and the size of the dot. Now, in order for the spin qubit to work, you have to remove all sources of noise. So this is why we perform our experiments in a dilution refrigerator at a temperature of 30 millikelvin. So on the top, I'm showing images of this dilution refrigerator, and the bottom is actually the device board where the chip goes. You also need heavy electrical filtering. So on the right, to remove electrical noise, of course. So on the right, I'm showing a electric schematic of our setup. So you can see that we have DC and AC signals. We have several filtering stages in the form of copper powder filters and RC filters, and also several thermal anchors. So let's talk about the fabrication. So on the right, I'm showing the falsely colored SEM image of the device that we actually fabricated. It is composed of 4 quantum dots made up of 2 double dots, one on the left and one on the right. And on the right, I'm showing a cartoon depiction of the same SEM image. Here, the color coding is as follows. Red is the accumulation and plunger gates. Green is the barrier and tunneling gate. Blue is the screening gate, and purple is the hafnium oxide layer. Beige represents the silicon and silicon oxide material. And at the bottom, there's a side view along the dashed line in the SEM image. So fabrication starts by first etching down the silicon oxide to 12 nanometers inside a window that's 500 by 500 microns. This is where the double dot will be formed. Next, we open up ion implanted regions to make ohmic contacts. So we etch down all of the silicon oxide in these regions. And now we'll focus on a very small region in the center inside the device window. So the device window is again shown on the top left, which again only has 12 nanometers of silicon oxide. We deposit a hafnium oxide next, and then the screening gate. All of the metal layers are made out of aluminum, and they're oxidized before the subsequent layer for electrical isolation. So the purpose of this isolation metal gate, or screening isolation gate, I should say, is to prevent any accumulation of electrons underneath it. That way, it restricts the accumulation of electrons along this long and narrow channel, and that's where we will form all our double dot. So next, we deposit the accumulation and plunger gates shown in red, and then the barrier and tunnel gates shown in green. At this point, we can form a 2-deck underneath the accumulation gates and double dots in the underneath the plunger gates. So these are all the steps for the fabrication. I'm going to now move on to the measurement results. We'll start with charge sensing. The reason why charge sensing is important is because it's a non-invasive technique, and it also has high sensitivity. The way it works is that you're using a single electron transistor or a SET sensor to detect changes in the electron occupancy of a single quantum dot that's nearby. And you have high sensitivity because the chemical potential of the SET sensor is very sensitive to electric fields around it, so that it can you can easily detect the additional removal of a dot in the transport data of the set sensor. So the setup is shown on the top left, where we see an SEM image. It's the same as before, I just rotated it 90 degrees. So on the top you have the set sensor, and the bottom will have a single quantum dot that we want to sense. On the right figure, I'm showing the differential conductance through the set sensor. And here, the important thing to see is that these nearly horizontal lines are actual single electron tunneling events. So if you take a cut along the y-axis, you would see the plot shown at the bottom in red, where each peak is again a single electron leaving or entering the dot. And we can actually detect the last electron, which is highlighted in the green circle. So if we focus on a single tunneling event, which is shown at the top, and we look at 3 different points along this tunneling event, we would see the waveforms shown at the bottom, which are again color-coded to correspond to the markers at the top. So for the blue and the red, the chemical potential of the dot is below and above, respectively. So it's below and above the Fermi level of the leads. And you see sporadic tunneling events because there's enough thermal energy that this can actually occur. And this is seen by the dips and the peaks in these 2 waveforms. For the black waveform, the chemical potential is actually aligned with the leads, so these tunneling events become much more frequent. The main point here is that we can actually detect single electron events as a function of time, and this becomes very important if you want to do readout measurements, as we will see in a few slides. So next I want to talk about the tunability of our device. So on the top I'm showing stability diagrams, which are transport data through our device as a function of the voltages on the plunger gates. So on the left we have a single dot underneath the tunneling gate, and the stability diagram has essentially these diagonal lines, which again they represent tunneling events. And if we control this tunnel gate, we can actually transition into the double dot regime. In the middle we now see these 2 slopes, which indicate that this is starting to occur, the formation of a double dot. And then on the far right we see that the stability diagram now has this honeycomb structure, which tells you that you have well isolated quantum dots. And in this case they would be underneath the plunger gates, as shown on the SEM image. Now a close-up of this last stability diagram, as shown at the bottom, really clearly shows the honeycomb structure, and these white lines essentially depict the boundary between charge configurations. These boundaries were calculated by fitting that experimental data to a model called the constant interaction model, and that's what I'll talk about next. So in this model you essentially use capacitances to model the capacitive coupling of the dots to metal gates and electron reservoirs and to themselves. So let's look at the stability diagram once again, shown on the right. So this is for a double dot. You have these cells that are stable charge configurations, and you have these orange dots that are called triple points because that's where 3 charge configurations meet. At the triple points, so for example at the red dot, the energy diagram would look like the cartoon on the left, so the chemical levels are aligned. If you now look at the green dot, they become misaligned. If you now apply a bias that opens up a window that's large enough such as the chemical potentials are within it, you would have electron transport. And if we look at the stability diagram, in fact when you apply the bias, what happens is that these pairs of triangles begin to emerge. And it's only within the triangles, which are called bias triangles, that you have electron transport. Outside of them, you're in Coulomb blockade and current is not allowed. So going back to the experimental data, if we fit it to the constant interaction model, we get capacitances that are a few attofarads, and the size of the dot it's estimated to have a radius of 40 nanometers. Now I'll move on to a charge pumping experiment that's supposed to show that we can perform pulse experiments, which again we'll see it's a very important tool. So in this case, what we want to do is transfer an electron from the left lead to the right lead. We do this, so the setup, first of all, is, as you see in the top left SEM image, we form a double dot at the bottom and the top device is not used at all, it's grounded. We'll measure current through the double dot, but we won't apply a bias. And finally, we use a pulse that's applied on the left plunger gate to transition the double dot between two states, as shown in the stability diagram and the two energy levels on the left. So during the load, what you're doing is you're allowing an electron to tunnel into the left dot. And during the unload, this dot is preferably going to tunnel into the right dot and then out into the right lead. So after one cycle of this, you've effectively taken an electron from the left and brought it to the right. If you perform this for several frequencies in the range of kilohertz and plot the measurable current, which is in the range of tens of femtoamps, then you see the expected linear relationship between the two. In this case, our efficiency was determined to be 83%. But this really highlights that we can indeed do pulse experiments. Now, I've said that we can do charge sensing and pulse experiments. The reason why this is useful is for single spin readout. So, for example, we can think of single shot readout using the Elzerman technique. In this case, again, we're using a pulse, which is shown at the top plot, the top figure. And this pulse is essentially going to take a single dot, in this case, from among three different states: empty, inject and wait, and readout. We also need a magnetic field to split the degeneracy of the levels inside the quantum dot, and we tune things such that during the readout phase, only one level is above the Fermi level of the lead, as shown on the top right image, and in this way, only when the electron has a certain spin state, in this case down, it can tunnel out of the dot, otherwise it won't. So if you now bring a charge sensor, you can detect this event, or not, by a blip during the readout phase, as shown by the red circle. So if you see the blip, you can infer what the spin state of the electron is. The only problem is that this is a destructive technique. The reason for this is that when the electron tunnels out of your dot, you lose it. You can't do anything else with it. So a solution for this is to use a non-destructive technique. Here we use a double dot and two electrons. The two electrons are now going to be in a singlet state, which has spin of 0, or a triplet state, which has spin of 1. This will become our new spin qubit, the singlet triplet qubit. So in this case, what we do is we tune our double dot into the 1-1 charge configuration, and if and we're gonna pulse into the 0-2 charge configuration. So if you started in the singlet state, in the singlet 1-1, and you pulse to the 0-2, this would be allowed because you're conserving the value of spin. However, if you start at the triplet 1-1 and want to go to the 0-2 charge configuration, the triplet 0-2 is usually at a much higher energy and it's inaccessible. So because you have to conserve spin, the electrons are forced to remain in the 1-1 configuration. So now, how do you measure the spin of your singlet triplet qubit? You bring a charge sensor. And essentially what you do is you go to the 0-2 configuration, and if you detect that you are indeed in the 0-2 charge distribution, then you're in the singlet state. Otherwise, if you are still in the 1-1, then you're in the triplet state. The key thing here is that because you're tunneling between the quantum dots, you keep the two electrons for further calculations or operations. So it's non-destructive. And I should point out actually that this phenomenon is where the triplet cannot tunnel, where the electron cannot tunnel if it's in the triplet state. Is called polyspin blockade. Next, I'll talk about a universal quantum processor. So this idea, I introduced it at the beginning. So here, what we want to think about is that if we wanted to implement again a 1D array of qubits with the scheme that I've sort of explained throughout the presentation, which is a metal gate defined quantum dots, then it would look something like the cartoon at the bottom. You have these gates that define your quantum dots, which are the orange spheres, And you need two requirements, as you may recall. We need arbitrary spin control of a single qubit, I should say. So you need to perform arbitrary single qubit operations, and you can achieve this through ESR. You can also have tunability of your ESR control through the Stark effect, which allows you to tune the G factor by means of electrical control, so voltages on the gates. And the two qubit entangling gate can be achieved by the nearest neighbor exchange interaction, which is again controlled through voltages on the gates. So you have the two ingredients for the universal quantum processor. And now you can bring in any of the readout techniques that I explained before. And so the thing to point out here is that this is where we're heading. This is what we want to achieve. We already have started implementing some of these things in the form of demonstrating charge sensing and pulse experiments, but we've also modified our geometry, which is shown on the SEM image. So now the layout is a little bit different, and this is to open up space at the top where we'll have an ESR line that will give us single spin control. We also are exploring different readout techniques. So one of them is called dispersive gate readout. It also uses polyspin blockade as before, but here we connect the double dot to a resonance circuit, and the spin state is actually inferred by a shift in the resonance frequency of the circuit. We implement the circuit with a superconducting spiral inductor, which is what I'm showing at the bottom left. Now, once you can implement a 1D array of qubits, then the natural thing to do is to implement a 2D array of physical qubits. The reason for this is that then you could implement a surface code error correction scheme where you have where the logical qubit is actually a 2D array of physical spin qubits. This is what I'm showing on the left figure. And the way the scheme works is that you perform parity measurements to a group of qubits inside your 2D array. This is sort of illustrated by the two colors in the left image. And these measurements essentially allow to detect if an error occurred during your quantum computation that you can correct, obviously. So then if you are able to do this, then you extend this to an array that is composed of blocks that are the same as the image on the left. So that's what I'm showing on the right, this sort of array of 2D blocks, where each block is essentially a logical qubit. So if too many errors occur which are represented by the block dots, then you just discard that logical qubit. So this scheme has already shown some promising results in superconducting qubits, and studies have shown that at about a 1% error threshold on your physical qubits, you can already achieve fault tolerance. So it's a very promising technique, and we want to get to this point. So a summary of what I've talked about. At this point, we can fabricate a 4 quantum dot device that is made up of 2 double dots, as I explained. We can tune this device through the interdot coupling to go from single to double dot. We can perform charge sensing and pulse voltage experiments. Now, some of the challenges that we still have to face are the number of gates or control lines, the density of them, which even at the stage that we're at can be challenging, and it has to be addressed if we want to think of scaling up to tens of qubits. There's also the fabrication yield. This is also always a problem because fabrication is always time consuming. There's a lot of steps and is very prone to error. And even when the yield is acceptable, then you have device imperfections and variability. This could be changes in the geometry or defects in the semiconductor. Now, an approach that has been surfacing over recently is to use machine learning and optimal controls to actually basically characterize your system and use all the flaws and defects of your system. If you know them, and you can actually control the entire system, then you can compensate for it. So in conclusion, I've talked about why quantum computation is so important and why silicon is such a promising platform for physical spin qubits. I've shown that we have device tunability, charge sensing, and pulse, and the ability to do pulse experiments, which is again very important for readout techniques. In the future, we want to and are already starting to implement ESR in our fabrication. We want to add ESR control for single spin readout. And no, I meant to say that we want to implement ESR control, and we're already beginning the steps by modifying our fabrication steps. And we want to implement single spin readout in the form of that is non-destructive, for example, dispersive gate readout. Our ultimate goal is then to create a qubit array, a 1D array, that would allow us to demonstrate universal control, and we can begin to think about implementations of quantum error correction and detection. So I'd like to finish off by acknowledging the members of my group that worked on this research and also the funding agencies that made this research possible. Thank you for your time.